I'm sharing my screen. Yeah, myself, Sanat Kumar. I have 15 plus years of experience in both academics and industry. So today I'm going to deliver the demo class. This is related to both physical design and ASIC verification. Okay. First Gnanodaya VLSI technologies. First we'll see the what are the job opportunities in VLSI and semiconductor industry. So these are the contents I'm going to deliver today. Okay. And next, so we'll see. So if you see the semiconductor industry, so basically semiconductor industry is divided into three main categories. Those are product-based companies, service-based companies, and EDA companies. So product-based companies are nothing but they will deliver their they will produce their own ICs. Okay, like Intel. Okay, ARM. Okay, and NVIDIA. Okay, Nvidia, okay, and Samsung. Okay, these are product based companies. Service based companies are nothing but they will not produce any product, just they will give the service depending on the whole product based company will do the whole VLSI design flow. So it will give some sub modules to the service based companies. So these service-based will companies will give the service to both EDA companies and product-based companies. And EDA companies are nothing but EDA is nothing but EDA, or we can call as CAD also. Okay, CAD means computer aided design, and EDA is nothing but electronic design automation. Okay, EDA is nothing but electronic design automation. So you already studied like SSI, small scale integration, and MSI. Okay, medium scale integration, large scale integration, and very large scale integration. Okay, and you have ULSI, okay, GLSI, okay, giant large scale integration. So that means here like 10 gates are there, 10 modules, 10 gates are there means SSI. Suppose the 1000 gates are there means MSI, and 10,000 gates are there means VLSI. So VLSI means what? You have some millions of transistors, some in terms of crores, 100 crores of transistors are there within an IC. Okay, so for that manually, when you are designing that, it is manually, it's impossible. You need to take the help of EDA tools. Okay, electronic design automation tools, electronic design automation. Okay, so automation. So the companies will which will provide these EDA tools are like Cadence. For the front end, you have Cadence tools, and the back end also you have Cadence tools. In the front end, you have Cadence, Virtuoso. Okay, Cadence Exilium. Okay, in the back end, you have Cadence Innovus tools. Okay, and Mentor Graphics also. Mentor Graphics front end, you have for the Verilog, you have Model Sim and Costa Sim, like that. And Synopsys also. For the Synopsys, you have front end VCS, Synopsys VCS, design compiler. For the synthesis, you have design compiler, like that. You have so many tools. These EDA companies will provide the tools. Okay, so this EDA and product-based companies and service-based companies, they will combinedly work together. So they will synchronous up to meet the technology deliverable. Okay, so that means whatever the technology, whatever the ICs they are making, they will combinedly work together. Okay, so with the support of what VLSI engineers. Okay, so VLSI means very large scale integration. Okay, we are in VLSI, so that is very large scale integration. Okay, hope you understood what is this VLSI companies will do. And coming to the physical design. So before this, I will tell you the basic design flow in the ASIC design flow. Okay, so if you see the ASIC design flow, here itself the physical design flow will cover. So ASIC is nothing but application specific integrated circuits. Okay, so VLSI target devices mainly you have both ASIC and FPGA. Okay, ASIC and FPGA. ASICs are nothing but suppose this will take low power, and once the programming is done, we can't change the ASIC. Suppose in your household applications, you have like LED TV, LED TV, smart TV is there. Smart TV is one ASIC, okay, and your washing machine, your AC, okay, and microwave oven, and so in the automobiles also, like you have airbags, anti-lock braking system, and engine control system. So that IC you are making for only particular application. That is nothing but IC. Okay. So again, FPGA is nothing but field programmable gate array. Field programmable gate array, it consists of some lookup tables, okay, LUTs, lookup tables, and configurable logic blocks, IO blocks, okay. So here, suppose in the digital, if you want to design some, let us take counter. So for the counter, you can write the Verilog code, and you can port you can convert that Verilog code into this bitstream file. That bitstream file you are loading into the FPGA. FPGA will work as a counter. Okay. So after sometimes you can write for FSM, some sequence detector, and that sequence detector program, if you are loading, the again FPGA will be act as a sequence detector. So that means you can erase the program. Okay, so mainly it consists of some SRAM. Okay, this is volatile. Still the power is there that we are using, and uh, mainly this is used only for the R&D purpose. You have FPGA boards like Xilinx boards, Altera boards. Okay, that boards, with the help of that boards, you are loading, you are porting, you are designing into this FPGA, and you can use for R&D purpose. Any times, any number of times, we can reprogrammable, reprogrammable or configurable. Okay, so this is the basic target devices. Okay, so first so this is ASIC flow. Okay, FPGA flow is different. Is that first I will tell you the ASIC flow. ASIC flow, first you will get the design specification. Design specification means first when you are making one IC, first that IC you are making for which application. That means you need to know. Okay, either you are doing this IC for computer application, or network related application, or defense related application. Okay, or telecommunication communication application, that you know. Okay, that you should know, and you need to know the power related, how much power it will take, how much area it will take, and how many inputs and how many outputs. Okay, that is nothing but specification. Okay, specification. Any module you are using, first they will give like a data sheet, no? Their data sheet, all the specifications will be there. So like that, any customer or client is coming with that specification. I need this many outputs, it will take this much of power, and clock frequency also. Clock frequency. So clock frequency means it should operate at some like 500 megahertz, 2 gigahertz. Okay, he'll give these specifications. Okay, higher level, there are architectural engineers. These are the higher level position. They have more experience, to 15 to 20 years experience. They will take the specifications from the client, and they will decide what type of design and how many inputs and how many outputs. That is comes under the design specification. Okay, and after that they will do the architecture. Suppose example, when you do the architecture, you are doing the making for CPU. Okay, so that means CPU IC. So you are making some, let us take Intel i7 processor, or AMD processor like Ryzen 7 or Ryzen 5. So this is architectural level. That means this is a system. This is nothing but system. So this again system consists of what? How to design this architecture. So it consists of some like ALU, okay, and you have memory unit, and you have bus interface unit, and next you have control unit. Okay, so this both total CPU architecture will be done in the architectural level. Okay, architectural level. After that, microarchitecture. Microarchitecture means these submodules are there now. ALU, my memory unit, and bus interview. This submodule architecture is divided in or done by the microarchitecture. So basically, there is a hierarchy level. Okay, hierarchy. Hierarchy means first, so mainly system will come, and next module will come, and next modules are made with gates. Gates are made with transistors. Okay, this is top-down approach. Okay, bottom-up approach means transistor, gates, modules, and systems. Okay, so in the VLSI, basically we will follow top-down approach. Top-down approach. First, we will come with the design specification, architecture, microarchitecture. Okay, and after that, there is a RTL design. RTL is nothing but register transfer level. Register transfer level. Okay, so RTL is nothing but I think you already studied about the digital. So digital, you have like combinational circuit or sequential circuits, FSNs, all those things are there, no? So here RTL is nothing but whatever the you studied in the digital, that you are means you are writing in terms of textual form, programming form, that is Verilog. You are using Verilog, or you can use VHDL also. Okay. VHDL is nothing but very high speed integrated circuit, hardware descriptive language. Mainly Verilog you are using. Basically, like you have like four styles are there. One is switch level modeling, and next you have mm, gate level modeling, data flow modeling, okay, and behavioral modeling. So when you are writing the program in the data flow and behavioral, switch level modeling means a low level modeling. You are writing for CMOS circuits. Gate level modeling means you are using some gate level primitives and or not, and that gate level modeling in terms of gates you are representing. Data flow modeling means you are writing in terms of expressions. Okay, suppose like AND gate is there. I'll tell you with one example. AND gate is there. So we are writing. So gate level modeling means and output y a b. So y comma a comma b, like this you are writing. So and next you are doing data flow modeling means y equal to you are writing in terms of expressions. Okay. Behavioral modeling means I know the behavior of the circuit. Okay, I'm not taking care of internal circuitry. You are using some procedural blocks like always and initial block and procedural statements like if else case and those you are using. So mainly you have like RTL engineers are there. So RTL engineers. So RTL engineers will design the your microarchitecture. Okay, RTL design. Okay. So basically you have like HDL. HDLs are the hardware descriptive languages. You have software languages also. Software languages like C, C++, Java, Python, and all those things are there, no? So these will not convert into hardware. Just they will develop the application only. Okay. But with the HDL, we can convert the program into hardware. That is gate level netlist. Gate level netlist. Okay. RTL design. And next, it will go to the RTL verification. Okay. So by using Verilog up to like FIFO or FIFO RAM, okay, single port RAM, we can write the Verilog code and we can verify by using test bench. Okay. But if you go for complex designs like SOC or system on chip or IP, okay, IP, you can't use this Verilog. You need to go for system Verilog and UVM. UVM system Verilog. So that will be done in the RTL verification. So you have so you need a, verification engineers for this, you need verification engineers. Okay, RTL verification engineers. Okay, these verification engineers they will use system Verilog and UVM. System Verilog is nothing but it's a advanced version of Verilog. They added some more features like it will follow two four-state data type, but it will follow two-state data type, and some more techniques like polymorphism, randomization, constraint randomization, and coverage, coverage will be there, and oops concept will be there. Okay, oops concept will be there. Oops means like you already seen in the C++. No, that means you have child class and parent class. Inheritance will be there. Okay, and so SV is a robust. That means you are writing the test bench only. For in using SV and UVM, you are writing the test bench for this design. Okay, so RTL engineers will design by using Verilog code, but this SV and UVM people, they will this verification people, they will write the test bench only. So SV test bench is robust. Suppose if you are writing for I2C, separately you need to write separately you need to write for UART. Okay, so it is time consuming, so that's why you need to go to UVM, that is universal verification methodologies. That is, this is not a language, it's a methodology. You are using SV in the UVM. There are some like so in by using UVM, suppose you wrote for the test bench for I2C, so by using simple methods you can, by some changes you can write in test bench for UART. Okay, so that is the flexibility is there in the UPM. So you want verification in it. So these two engineers will work together. Okay, so RTL engineers will design the module or micro architecture or micro architecture, and RTL verification engineers will verify whether your circuit is means working properly or not. They will see each and every corner cases also. Okay, like in Verilog, there is a block box verification will be there, but in the system Verilog or UVM, you have white box verification will be there. Okay, and if design is met, it will go to the next step. If design is not met, it will go to the again RTL design. Okay, again you have logic synthesis is there. So logic synthesis means these synthesis people are there. These synthesis people, so here you have formal verification also. One more thing, one more formal verification. Formal verification means what? They will use some mathematical tools or mathematical formulas to verify your design. Okay. Design verification means you are using by using this SV and UVM, but formal verification means they use some mathematical tools. Okay. And synthesis engineers are there. Synthesis engineers means they work under these constraints. What are the constraints? Means ATP, area, time, and power constraints. Okay, ATP constraints. There are some they will work under the some these constraints. They need to like when you are doing this after verification, you are getting unoptimized design. Unoptimized design. Okay, after synthesis only you will get a optimized design. Optimized design. Okay, DFT is nothing but you have DFT engineers also. DFT is nothing but design for testability. Design for testability. Design for testability means they will test whether your design is meeting the specifications or not. Okay, so they will use some scan test. Okay, built-in self test. Okay, some techniques they will use and they will test your design. Okay, and LEC is nothing but logic equivalency check. This is nothing but logic equivalency check. Okay, so logically they will check the equivalency whether your specification is meeting or not. Okay, and STA engineers are also there. STA engineers. So STA engineers, static timing analysis. Static timing analysis. Okay, so static timing analysis, they work under like timing, like suppose in the digital you already studied AND gate is there. So AND gate, you are getting the inputs A, B, and output Y equal to what? A and B. Okay, this is you are getting the output at zero simulation time. Okay, but there will be some delay for the AND gate, that is propagation delay. Okay, there is some propagation delay. Okay, so we'll study about delays, setup time, hold time, and violations, setup violations, hold violations, and some these things. Okay, these things will they will do work under the STA. Okay, this is one type of simulation only. So in the here we do the simulation by using waveforms. But with the help of this working under the delay related, timing related things, they will use in the static timing analysis. Okay, uh, like that. Okay, and if design is met, if design is not met, again it will go to the synthesis. Again, if design is met, it will go to the PD flow. Okay, so PD flow. So PD flow, you have partitioning. Okay, PD is nothing but physical design. Physical design. Okay, physical design, partitioning, floor planning, power planning, placement, clock tree synthesis, routing, and timing closure. So partitioning means it's like constructing a building only. Okay, this PD engine is, so till here. Let us assume this is front end. Okay, front end. So the PD people will take the input from the front end people, and they will make the ICs. Okay, they will partition, like they partition into different groups. And floor planning, floor planning. This will discuss clock tree synthesis, routing, and time enclosure. That will be done by the PD engineers. Okay. So here you have PD engineers. Okay. So PD engineers are there. PD engineers. Okay. And next you have so physical design. Physical design is a backend. Okay. Physical design is backend. Parasitic extraction means they will design like we came across the technology, 900 nanometer technology, 250 nanometer, 22 nanometer. Now we are working under 3 nanometer technology. So that nanometer technology is nothing but the distance between source and drain and channel length. Okay, for the MOSFET, the channel length. Okay, assume that means how many transistors are there. So this much of length is there. We can't see the one transistor with our naked eye. Okay, and between this transistor, one transistor layer, other transistor layer, there will be some wiring will be there. Metals will be metal wiring is there. So for that metals, you need some, you have some resistance and capacitance, RC extractions. Okay, RC extractions are nothing but parasitic extractions. Okay, so you need to evaluate how much of a resistance and capacitance will be there for the metal wires, inside the metal wires. All those things you need to see in the parasitic extractions. Okay, and post layout STA. So STA will be preload STA and post layout STA will be there. After PD flow, again you have post layout STA. Okay, and if design is met, it will go to the next step. If design is not met, again it will go to the PD flow. Okay, and next, physical verification. Physical verification means so verification will be done in the front end, as well as after that, after PD flow, parasitic extraction, and post layout STA, verification done in the back end also. Okay, this verification whether your chip is meeting the specifications or not, and they will check all the electrical, physical, and all those verifications they will do. Okay, this will discuss. And fabrication. Fabrication means here they will produce GDS2 file. GDS2 file. Okay, so GDS2 file will be given to the fabrication. So fabrication, the fabrication people, what they will do, they will do the fabrication by using like N-weld technique, twin tube technique. So many techniques are there, like diffusion and implantation, photolithography. Okay, and metallization. Okay, etching. Okay, all those things will be done in the fabrication. Okay, so like this, if you see, so total like 10 to 15 VLSI engineers are required for total flow. Okay, total flow you need 10 to 15 VLSI engineers. Okay, so this is about the ASIC design flow. Hope you understood. And next, coming to the physical design, like floor planning is there. Floor planning means what? You are planning for the floor. So that means a die will be there. Okay, there will be die. It's like a die. In the die, you can make so many processors and modules you can make. It's like it's the die will look like this. It will be notch type or flat type. This it's like a CD type material. This is nothing but die. Okay, die size estimation. Okay, they estimate the die size and IO and macro placements. So edges there will be IOs and macros. Macros are nothing but RAM. and SRAM and I2C. These are nothing but some macros. Okay, how the macros are placing. Okay, and they will plan for the power distribution also. Okay, so here what are the goals for floor planning means when you take the physical design, you are going to study in detail. Just I am giving some rough idea. All macros in placement grid, no macros overlap, no PG nets or DRC. Design rule checks are LVS, layout versus schematics. Okay, minimize the conjunction, make sure design timing is met. There should be uniform area placed in the standard cells. Standard cells are nothing but those are like predefined cells. They have a fixed area and timing will be there, and those are available in terms of AND gate, NAND gate, NOR gate, and NOR gate, and half adder, okay, full adder, and D flip flop. Okay, like that, standard cells are available. Okay, so those placing is in the floor planning. That is there in the physics floor planning. Okay, so what are the inputs for the PD means? These are the inputs. Gate level netlist. I told you, no synthesis. By using synthesis, we can convert our code, whatever the Verilog code after verification and all those things. We'll convert into gate level netlist. The circuit is in terms of gates. Okay, that is .v file. Okay, and from the synthesis, you'll get HDC files. Okay, uh, these are nothing but synopsis design constraints. Okay, these are the constraints. Okay, so constraints are nothing but related to area, time, and power. These are the constraints. Okay, and logical library cells. Okay, logical library cells means in the library cells, like this synthesis or this whatever the Verilog code you are writing for the digital modules. Suppose some analog blocks are there, like IO blocks, 5 blocks, or like clock dividers, like PLL. That will be available in lib file, library file. Okay, logical library and physical library. Okay, physical library and multi-voltage domain designs, UDF files. These all files will be taken by the PD people from the front end. Okay, on the front end, and they will do floor planning. So floor planning means, as I told you, estimating the die size, okay, and minimize the core area, okay. So like, so they will work under different technologies. So that means in VLSI there is a Moore's law is there. No, Moore's law means what? Transistor count doubles for every 18 to 24 months. So that means here you need to increase the transistor count, and within that area you need to make the technology. So that means you need to make with 7 nanometer technology or 5 nanometer technology or 3 nanometer technology. Okay, the technology you need to make. Okay, and planning the core area for different IPs. I told you, IPs, intellectual properties. Okay, IPs. Okay, like USB block, video block, display block, or DDR block. We need to make the blocks. Okay, so where it should come, and these are IO blocks. Okay, planning for IO pads, power planning. All those things will be done in the floor planning. Okay, where the macro cells will should come. Okay, where the IP block should be placed. All those will be done on the floor plan. Okay. IO planning means uh, we can receive three different types of inputs from FE regarding IO ports. What are these? From the def file, from IO assignment, and these specifications. So based on this, we need to do some IO plan. Okay, so we need to do this IO planning. And floor planning means what are the floor planning area means core area and die area. Okay, so core area means this is my core area total. This is my core area. So where I need to keep the standard cells or macro cells. Okay, and die area includes the core area and IO cells. Total die area. Okay, core area includes the standard cells and macro cells, and the die area includes the total die area. Okay, the total die area, core area. Okay, die area. So placements are so what are the, so it gives the exact location in the core area. All standard cells is called placement. So all instances soft modules are placed in the core area. So what are the goals? Less utilization gems, no conjunctions, no overlaps, good timing values. So all those will comes in the placement. Okay. Clock tree synthesis, there will be a global clock. So each module will not operate at the same clock. So the inside there will be PLLs are there. PLL will divide, it will multiply the clock, and the clock dividers will be there. So you can do for this clock. This is CTS, clock tree synthesis. Okay, wherever the clock is dividing and all those things will be done in the clock tree synthesis. Routing is nothing but connections. You need to do connections. It will creating the global or track routes, connections made between signal pins and metal layers. Okay, signal pins and metal layer. There will be some layers will be there. One after the other, layers will be there. Inside that, in that layers, transistors will be fabricated. Okay, logical connectivity and physical connectivity. Routers try to fix a DRC. Okay, so these are routing. Sign off checks and verification means, as I told you, verification you need to do for electrical verification, physical verification, and crosstalk. Okay. So in electrical verification, you need to do power estimation, IR drop analysis, power EM, signal EM, and physical verification, you need to do layout versus schematic, design rule checks, and antenna checks. All those things will be done in the sign off checks or verification. Okay. So this is about the both all physical design back end. Okay, coming to the front end, design verification. Okay, so front end, wherever you see VLSI is there. Suppose you are using microprocessors in the computer, personal computers, and graphic cards, digital cameras, com cards, chips in cell phones, embedded processors, safety, like I told you, in automobiles, anti-lock braking system, automobiles, personal entertainment system, medical devices, all the wherever you see VLSI is there. Okay, so VLSI is there everywhere. So you already studied about in the BTech microcontroller, microprocessor. Okay, this is SoC, system on chip, and this is FPGA, field programmable gate array. So microcontroller is nothing but you have one CPU will be there. So within an IC you have CPU, ROM, serial interface, RAM, timer, and IO ports within a single IC. Single IC. So I think you already studied about the basic 8051 microcontroller. It's a 40 pin IC, and it consists of 4 kilobytes of ROM and 28 bytes of RAM, and two timers are there, and three ports are there, four ports are there. Like that, you already studied. Okay, you have 1 megahertz to 300 megahertz clock rate will be there. Okay, mainly in the embedded systems we are using these microcontrollers. Okay, so I2C, UART, SPA. Okay, that we are using in the microcontrollers. Okay, microprocessor means what? It consists of ALU, register array, and control unit. Okay. So ALU performs arithmetic and logical operations. Okay. Whatever the data is there, that will be stored in the memory. Memory is separate only. You have for temporary processing purpose, you have register array. I think you studied about 8086. It has a 20-bit address lines and 16-bit data lines that you already studied in the BTech. Okay. 1 gigahertz. So what is the clock rate? 1 gigahertz to 4 gigahertz will be there. Microprocessors and system on chip. If you see, system on chip is an integrated circuit that compresses the required components on a piece onto one piece of silicon. Whatever the required components are there, that is there in the one piece of silicon. Okay. Why we are using means it eliminates the need of separate or larger system components. Okay. Suppose within the board you have data processing unit, embedded memory, graphic processing, USB, video and audio processing. All those are there in the system on chip. Suppose if you see here, ARM processor is there, and voltage regulator is for giving the voltage, DC voltage, SRAM, flash, and application specific logic. You have PLL oscillator, RC oscillator, reset circuit, all those things. Ethernet, MAC, USART, SPI, two-wire interface, ADC, PWM, USB device. Okay, all this timer 0, timer 1. So all these are there in within an IC, like Raspberry Pi. Raspberry Pi is one SoC, and your i7 processor or Ryzen 7 processor. Okay, Ryzen 5 processor. All these are nothing but within one SOP. So how they are connected means this is also important. These are connected by using AMBA protocols. AMBA means advanced microcontroller bus. Okay, so you have like in this AMBA, you have AHB bus, advanced high performance bus. So this is used to communicate between the high frequency signals. So processor is a high frequency signal. No? So these are high frequency signal, and there is a peripheral bridge, APB. Okay, advanced peripheral bus. This is used to communicate between the low frequency signals. Okay, between the low frequency signals. So these are the AMBA protocols. Internally, that will be connected with the AMBA bus. Okay, AHB and APB bus. So FPGA, if you see, so FPGA can be configured many thousands of FPGA. I told you, no, it can be reconfigurable, reprogrammed. It can be reprogrammed. We can program this FPGA. Okay, so it consists of what CLBs are there, configurable logic blocks. Okay, CLBs and IO blocks. Okay, in the CLBs, like you have some mux will be there, and one D flip flop is there. Okay, D flip flop, mux and D flip flop, and lookup tables also there, LUTs. Okay, from the LUTs it is given to the mux, and one more input is given through the D flip flop, and you are getting the output like that. Inside a CLB, these will be there. Okay, mux and D flip flop is there. One input is coming from the lookup table, and one input is coming from the D flip flop, delayed input. You are getting the output. Suppose if you want to write for D flip flop, you can write the Verilog code or VHDL code that bit stream is there that you are loading into the FPGA. This FPGA is acting as a D flip flop. So mainly we are using for R&D purpose only. This FPGA we are using for R&D purpose, mainly in defense. FPGA is used in defense, and the cell towers will use this FPGA. Okay, why? Because here technology is changing means we can't purchase the weapons. No, weapons are very costly. So when you fabricate with FPGA, any technology is changing means we can make programmable in the defense related things. Okay, cell towers also day by day you have initially 2G is there, 3G is there, 4G is there, 5G is there, future is 6G. Okay, so when technology is changing, we can't change whole equipment. No, so inside that cell tower, if FPGAs are used, so based on the technology, we can change the programming. Okay, so these are the applications of FPGA. So this VLSI design flow I already told. So we already see in this VLSI design flow. Okay. Mm. So here what happens? Different steps are there. All EDA tools can import or export the different files type to help the making flexible design flow. Okay, that uses multiple tools from different vendors. Okay, for the front end you are using different tools. For the back end you are using different tools. Mainly you are using like Cadence, Synopsys, Mentor Graphics, and AMD also. From the AMD Xilinx Vivado we are using for the Verilog and synthesis. For the simulation and synthesis, we are using that model sim, Quasta sim, and Cadence, in-house tools. All those things we are using in the design flow. Okay, in the design. Okay, VLSI design. So I told you, know what are the target devices, FPGA and ASIC. ASIC stands for Application Specific Integrated Circuits. It is especially used for only specific application. Okay, compared to other devices. It is improved in the speed. Okay, basically in the integrated circuits we are using for one specific purpose. That is ASIC. FPGA is nothing but field programmable gate array. We can reprogram any number of times. We can reprogram. Okay, it consists of what collection of hundreds or thousands of gates are there. Okay, and to build the complex digital circuits. Okay, so we can program by the user any number of times. Basically, FPGA we are using for R&D purpose. Okay, this we are using for specific application, our household, like daily applications. Once the program is written, Means ASIC, these chips, if you see, when you are using the ASICs in a smart TV, that so same ASICs we can't use in the washing machine, okay, or we can't use in the AC, okay. That is only used for specific application, okay. That is ASIC. So this is the FPGA flow. I told you, Xilinx Vivado. This is a tool, Xilinx Vivado tool. Uh, so HDL can be achieved. So hardware descriptive language. HDL can be achieved by two. One is a Verilog and VHDL. VHDL is very high speed integrated circuit hardware descriptive language. So this Vivado tool converts this our code, HDL code, into schematic. What is that schematic? Netlist. So that I told there is a term called synthesis. Synthesis will convert your code into netlist. Okay. After that, there is a implementation will be done. What is implementation? In the implementation, so you need to do the translate, map, place, and route. Okay. So that means floor planning, routing, placement, and mapping will be done in the implementation. Okay. So after that, bit file generation. So it will generate the bit generation, bit file generation. This bit file you can port into the FPGA. Okay, bit file you can port into the FPGA. Okay. So like in the embedded lab also, you used some microcontroller board, no? Microcontroller board. Okay, there also you are writing assembly language program. When you are doing for some LCD or LED or 7 segment display or stepper motor, like that you are writing. At last you are generating the X file. That X file you are loading into your microcontroller. So based on your application, your microcontroller or microprocessor will work. Same like that. Here you are generating bit file generation. This is in terms of zeros and ones. That we are loading into FPGA. Okay. This is FPGA flow. So there are some design closure techniques are there. That is functional closure, power closure, and timing closure. So functional closure means so here through simulation, functional closure can be achieved. Through simulation means waveforms. Suppose if you are designing like if you are writing the code for half adder circuit, first you need to write the design and next you need to write the test bench. In the test bench, you are giving the stimulus, applying the test vectors. So by applying the test vectors, you know that. So that means for half adder, you know that sum and carry. You know that 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, and 1, 1, 0, 1. You know, but how the design will know? You need to write the test bench and you need to do. You need to see the circuit through the simulation waveforms. Simulation is nothing but by using waveforms you need to see. Okay. Power closure means like proper timing closure will enhance the power efficiency. Okay, that is power closure. And timing closure means you need to work with static timing analysis. That is timing closure. CDC, clock domain crossing. Different clocks are there. You need to work with CDC. So in digital, you are worked under only one single clock, but multiple clocks are there. There you will get the CDC, clock domain crossing, and reset related things are there. You need to learn about reset domain crossing, reset RDC is nothing but reset domain crossing. So, suppose if you see the course overview, there are two courses in the front end. One is RTL design, next is ASIC SOC verification. In RTL design, the basic will teach you the digital electronics. Verilog will teach you. Okay. Why will teach Verilog? I will tell you. Verilog projects will provide, and STA, CDC, and RDC will teach, and Lenting also will teach. This is RTL design. Suppose if it is a SOC, ASIC SOC verification, will teach you digital electronics. Verilog will teach, okay, and Verilog project will give, and STA will teach. STA will teach, okay, and SystemVerilog will teach SV. SystemVerilog assertions will teach, and UVM also will teach. Okay, so that is related to ASIC SOC verification. Okay, and coming to this Verilog and VHDL. So Verilog, if you see the Verilog, so this is high level language, easy syntax, easy to learn, and multi-level abstraction. Okay, this Verilog is universal. This Verilog is universal. Wherever all over the world, RTL engineers, RTL engineers for ASIC, they'll use Verilog only. Okay, they'll use Verilog only. So if you see, so why it is easy? So this will follow C syntax. If you are comfortable with the C, you can easily learn the Verilog. Okay. Suppose this is a AND gate. Inputs are A, B, output is A and B. Okay. So how to write the Verilog code? Module, and this is my module name, or we can call as identifier also. Identifier. Okay. And underscore gate. Okay. Input A comma B. Okay. Output Y. Okay. I'm using data flow modeling aside. Okay. Previously I told you, no, RTL design. RTL design means you need to write the Verilog code by using two modeling styles. One is data flow modeling, and next one is behavioral modeling. Okay. So here I'm using a assign keyword. So this is nothing but continuous assignment statement, a keyword called assign y equal to a and b. Okay. So this is nothing but bitwise and operation and end module. So that means within three lines my and gate code is completed. Okay. Coming to the VHDL. Okay. What is the full form of VHDL? Very high speed integrated circuits hardware descriptive language. Okay, so you're describing the hardware in terms of textual form or in terms of programming. That is nothing but HTL. Okay, hard syntax is there, controlled language, hard to learn, and multi-level abstraction. Okay, so see here, suppose you need to use a header file library IEEE. Use IEEE.std logic 1164.all. You need to create the entity. In the entity and underscore gate is port A in HTTP logic, B in HTTP logic, Y out HTTP logic, and gate. Okay. In the architecture, you need to write the logic. Architecture of and underscore gate is begin Y equal to. Here you given the symbol. This is bitwise AND gate. Here you need to use AND like this. Y equal to A and B and architecture. So it will take around 12 lines, lines of code, I think. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines of code. It will take around 12 lines of code. So this is mainly, this is used in defense purpose. Okay. So this is standardized around 1999, and this Verilog is standardized around 2001. Okay. There is a governing body, that is IEEE. IEEE makes this as standardized. Okay, Institute of Electrical and Electronics Engineers. Okay, you'll do the projects by taking the IEEE papers. No, so like that's this is the difference between Verilog and VHDL. So this is analog layout. Analog layout, we will study about the basic layout related, like floor planning, placement, matching and page DRC, routing, design rule checks, layout versus schematic, post layout simulation, and tape out. All those things you will study about analog layout. Okay. So floor planning. So how the floor planning is there. Okay. Placement. So placement is nothing but CMOS circuit. This is my schematic. Mainly schematic is nothing but CMOS circuit. So how we are doing this placement and matching? This is layout. Okay, this is my layout. In terms of stick diagrams only, you are doing the layout. Okay, layout and placement matching and base DRC. Okay, this you'll study in the analog layout. Okay, routing also. Routing is nothing but same connections, global track routes and all those connections you will study in the analog layout. DRC, design rule checks. Okay. common errors below are the nothing but some common errors. Okay, I told you, know, within an IC there are so many metals are there, like N-well technique. The N-well means this is a fabrication technique. So AA layer, metal 3 layer, metal 2 layer, and metal 1 layer. So all those things you will work under the tool, cadence tool. Okay, two main process makeups of LVS flow. So common LVS issues you can see. Analog layout concepts means basically you'll study about CMOS fabrication, electromigration, IR drop, antenna effects, crosstalk, deep N-well, latch-up guard rings. Okay, latch-up is nothing but like when you are using a CMOS circuit, so there is a short path between this two VDD and supply voltage. So in order to avoid that, you need to use latch up the guard rings. You need to make the guard rings, well proximity, HTI, short channel effects. So short channel effects means when you are shrinking your transistor day by day, you are in a 3 nanometer technology. Okay, so previously like 900 nanometer or 450 nanometer or 45 nanometer. Okay, so 7 nanometer. Okay, so as transistor is shrinking, some problems are coming. Okay, that your study about the problems. Okay, like mm, impact ionization, hot carrier, okay, drain induced barrier, and all those things. Okay, LOD, standard cells, memory layout, analog blocks. That we will study in the analog layout concepts. So this is AMS is nothing but analog and mixed signal. So we are studying about the basic analog and digital. Okay. So VLSI is nothing but what combination of both analog and digital. So analog people will do this analog layout, and digital people this ASIC design flow I told you, no. Digital people will do this digital related the flow. Okay. At last they will combine this analog and digital. Okay, both analog and digital, and they will make an IC. Okay, that is AMS, analog and mixed signal. Mixed signal, that is AMS. Okay, so this is fully developed analog RF layout. So this we already discussed the chip design. Chip design we already discussed. So coming to the Gnanodaya, it's a premier institute for advanced VLSI studies, mainly located in Martali, and it's there in Hyderabad also. Hyderabad in SR Nagar, it's there near to metro station. So it's there both in two locations. One is in Bangalore, that is near to Martali multiplex Martali multiplex opposite, and in the Hyderabad, SR Nagar it is there. Okay, near to walkable to the SR Nagar metro station. However, the faculty trainers are there, are they are 15 plus years experience in semiconductor domain, and proven track record for the placement with scholarship facility will be given. And what are the unique features means 100% placement assistance will give, and industry standard course curriculum. Whatever the curriculum we prepared, that is related to the standard industry standards only. And VPN support will be given. So 24 by 7 lab support will be given. We'll give some login credentials. You can work under the tools. Okay. And low cost value for money. Okay. And so career guidance, if you see, first any requirement is coming. First we'll get the requirement from the client, and we'll assist the student preparation resume as per requirement. We'll send the resume to the uh, concerned client who are hiring. After shortlisting, so we make the student to attend the interview, and after that final announcement. Okay, this is 100% placement assistance. So parallelly, we will provide weekend assessments and assignments and modules also. Like parallelly, we'll teach the modules, and during module one module is completed. Suppose example, digital module is completed. In order to develop your communication skills, we'll parallelly give the topics in the technical, technical that means digital. okay, to make them to perfect in that concepts, and parallelly we'll give the after completing the technical seminars, we'll make you to give the technical seminars. After completing the technical seminars, we will give some topics related to aptitude also. Aptitude also very much important. Why? Because in the written test they are giving some 10 to 15 mark for aptitude. So we need to give the seminars in the aptitude also. So that this is a continuous process. Why? Because we are making you to develop the communication skills and how to mock interviews also there. So mock interviews with the play with the trainers. Okay. Suppose the students are there in the Hyderabad, we'll provide the mock interview with the trainers present in the Bangalore. Okay. So like that, the shuffle will be there. Okay. So this is continuous process to improve your. We are getting ready for you for interview. And as I told you, like these are the product-based companies like Samsung, Intel, TSMC, Micron, Qualcomm, Nvidia. Okay, these are like 20 product-based companies are there all over the world, and these are service-based companies. I think some of the companies you know, Wipro, Capgemini, Infosys, SCL, L&T, okay, uh, Capgemini, yeah, USD Global, okay, Graphene, Samsung, Open Silicon, Mindtree, Mirafra, okay. Apart from this, more than 1,000 plus service-based companies are there in the Hyderabad, Bangalore, Noida, and India, okay. Eligibilities, you should be BE BTech in EC and Triple E. Why? Because in the basic module, we are teaching the analog electronics that covers semiconductor physics, PN junction diode, MOSFET and CMOS, digital electronics also, okay, TICL, STA, okay, and DFT, synthesis, okay, fab, these are the common subjects for all the modules. So to know means you should have the idea about this electronics. You already studied in the BTech, no? So if you have the knowledge, we are again making you to refreshing that concepts. Okay, so these concepts are very much important. So suppose if you are going for PD, you should be strong in analog. If you are going for front end, either it may be RTL or DV, you should be strong in the digital. Okay, should be strong in the digital. It's like a Bible. Okay, should be strong in the analog as well as analog for PD people, and digital also will teach for PD people. But compared to digital, analog you should be strong. Okay, you are mostly working under CMOS circuits. CMOS circuits, that backend tool related floor planning and so here DV and RTL means mainly Verilog, SystemVerilog and UVM verification related. So you should be strong in the digital. Okay. TICL is the scripting language. STA means I told you, no, like timing related. DFT is for testing and synthesis for ATP, area time and power. So you should be graduate ME Tech, okay, in VLSI or electronics. You should be minimum 60% score in the graduation. Good communication skills, okay, good communication skills are required. These are the eligibility criteria. First, registration process. So the training process will be registration process. Discussing fee and course, training period, preparation with mentor support, conducting mock interviews, 100% placement assistance will be given. So these are the top companies for placement support. Multinational companies like Intel, Qualcomm, Micron, Samsung, analog devices. Okay, like that. Okay, and EDA companies. So as per our MD sir, on February, Intel and AMD is coming to our institute to hire front-end people, DV people. Okay. EDA and tool companies, Ambient, Ion, Synopsys, Insemi, like that. Indian startups also, eInfochips, Mirafra, service-based companies, TCS, Capgemini, Sankalp, Wipro. Okay. So these are our students like Amar Gopal. Amar Gopal placed in Apex. Okay. And Reshma. Okay. Reshma placed in HCL. okay, and Gaurav Sehwal. So these are our successful students. So these are some hiring companies: L&T, Capgemini, okay, Ambient, Simulus, all those. These are some successful students placed in companies. Okay. So training methodology and intake. So mainly there are three training modules are available: physical design, analog layout, ASIC verification. So physical design is 6 months. This is 4 months, 4 months of period. Daily 1 hour class will be there, and if it is weekend batch, 6 hours per week will be there. Intake is 15 to 20 only. Intake is 15 to 20. VPN lab support will be there, and the trainers are 15 plus years of experience. 100% placement support will be given. Okay. So this is the training methodology for remaining same only. And so if you want the course, you can contact this number and email also. This is website and the app is also available. You can install Gnanodaya app from the Play Store or App Store. Okay. So you can contact for anything. Okay. Yeah.